All right, well, welcome to Lecture 18 in Topology. We're talking about quotient topology today. So I'll begin with a few pages on what Minetti calls identification. I think other people usually call it a quotient map. So here's what it is. A continuous and onto map, or surjective map from topological space X to a topological space Y is called an identification, or a quotient map if the open sets of Y are precisely the subsets A of Y which have inverse images which are open in X. So it's a little bit slippery. Like, I don't know, I think there's got to be a better way to word that, but I haven't found it yet, but well, anyway, we'll see what that means, okay? So it's stronger than continuity for one thing, right? Because f is continuous, that's not a good sign. It's continuous if for each open subset of the codomain, you have the inverse image of that set is open in the domain, right? Now, it's on the other hand not as strong as the condition that f is an open map. See, open map would say that the forward image of any open set in X is open in Y. And that's not what this is saying either. So in fact, we'll see that there exist identifications which are not open maps. For example, number 2 from page 143 of Moncrief's Topology, first course, first edition, I think. I think I put that down as my example 3. We'll get to this here in a second. That's actually included in this lecture if you're curious. Okay, so identifications can be characterized by closed sets just the same because the inverse image plays nice with complement. So it's also the same. You could say that if the closed sets of Y are precisely those subsets C of Y which appear as inverse images of some precisely the sets for which the inverse image of those sets are closed in X, well then F is an identification. All right, so other terminology we should mention, but it doesn't seem like he continued. Well, I don't know. You can use it if you like it. I'm just mentioning it. So anyway, here we go. For f from x to y continuous, a subset of x is f saturated. If whenever x is in a and y is in x, and you have f of x equals to f of y, well, that implies that the y is an element of a. In other words, f is f saturated if the subsets of X are precisely those sets which arise. Words, goodness gracious. F saturated subsets of X are precisely those sets which arise as inverse images under F. In other words, A is equal to F inverse of B for some B. That means A is F saturated. So another way to think about it, a set is saturated if it contains any part of a fiber, it contains the whole fiber. Like, you can't have like a little bit of a fiber in the set and a little bit out. If you had that, it wouldn't be saturated. So saturated sets are, I can think of them sort of as being glued, like the fibers of the map glued together would give me a saturated set, something like that. Minetti says on page 87 that saying F is an identification amounts to saying that the open sets in Y are the images, exactly the images f of A of f saturated sets A. And then Minetti gives this example. He says let A be the cover. Let me zoom in a bit. It's writing kind of tiny here. Let A be the cover of a space X and consider the disjoint union of the cover equal to Y. All right. Then f from y to x given by f of x equals to x for all x and y is a continuous surjection. And for f to be an identification, we need the open sets of x are precisely a subset of x such that f inverse of a is open in y. But for this function, f inverse of a is equal to a, and so Minetti claims that f is an identification if and only if a is an identification cover. Remember, we talked about identification covers back on page 72 before we talked about compactness, remember? an identification cover was one for which U is open if and only if U intersect A is open for every A in the identification cover. So if you sort through that, then F being an identification is tantamount to A being identification cover, where here we're taking F going from the disjoint union of the cover to X. So I don't know, what's a good way to think of disjoint union? Disjoint union, I could think of it sort of like tearing apart the space X into little little bits of little sets called A, and then you kind of just take those sets and kind of set them, like, I don't know. So if you could imagine, just a stupid example, but if you can imagine a space which is just literally these two keys, right? And then the two keys are forming the open cover. Well, the disjoint union of that space would be something like this. So you're duplicating. I mean to say, you're duplicating. If the sets overlap, you don't like take and put one. You don't take the overlap sort of duplicates itself in the disjoint union. Like, it's not like before you could think of maybe I had just one copy of the sort of the head of the key, but then if I take the disjoint union, I get two copies of the head, one for this piece, one for that piece, and it's a disjoint union. They're disconnected. Okay. Anyway, disjoint union is kind of a weird thing. I sometimes am tempted to think it's the Cartesian product, but it's not quite that. So, but anyway, if you're curious, you can look it up. It's one of those things you can construct set theoretically from base principles. But I think I'm going to try to keep going here and get to the interesting part of the story. So, all right. So next up here, come on, here we go. Whoop. All right, let's try this again. Take my future pages, put them over there. Current page here. Zoom back out a little bit so I don't lose anything. There we go. All right, so a closed identification is an identification which is also a closed map. An open identification is an identification which is also an open map. Lemma, if you have F a continuous surjection, and if F is a closed map, then it's a closed identification. Likewise, if F is open, it's an open identification. So the proof is pretty simple. If F is surjective, that implies that F of F inverse of A is equal to A for any A in the codomain. Suppose F is open, right? And A is a subset of Y, such that F inverse of A is open. Well, then A is equal to F of F inverse of A, and that's open. Therefore, we just saw that any set in the domain which appears as the I don't even have the words for it. Goodness gracious. This is exactly what we need for F to be an identification, right? Sorry, it just does not stick in my brain at all. Anyway, a continuous and onto map F is called an identification if the open sets of Y are precisely the subsets A of Y, such that F inverse of A is open in X, right? So we took an open set in Y, right? And open set in Y, and then we looked at what the F inverse of A, precisely such that X. All right. Let's see here. F is open. A subset of Y. Okay, so F such that F. So we're assuming F inverse of A is open. So we're not assuming A is open at the start. We're assuming F is an open map, A is a subset of Y, and its inverse image is open, all right? But then A is equal to the image of the inverse image. And since this is open, and this is an open map, it follows that A is open, therefore F is an identification. Right, duh. Okay, It's not complicated. You just got to remember what the words mean here. And the same argument goes through for closed, because if f is closed and c is a subset of y, such that f inverse of c is closed, then c is f of f inverse of c, but this is the image of the closed image of a closed set, which is by definition closed, which means c is closed, which means f is an identification. All right, so now this right here is an example of a closed map. All right, and so we take a function from the closed interval from 0 to 2 pi to the unit circle given by the usual parameterization. Well, 0 to 2 pi is closed and bounded. In fact, it's compact, of course. And S1 is a Hausdorff space. So by corollary 4.2, that means that this continuous function is a closed map, in fact. Therefore, this is a closed identification. And, well, you know, it's also clear that this is onto, right, by trigonometry. So therefore, it's a closed identification. But it's perhaps an interesting example because while this is an identification, it's not an open map, right? So you might wonder, okay, well, you said not every identification is an open map, right? Well, here's an example of one, because 0, 1 is open by the subspace topology of 0 to 2 pi, but the image under the parameterization map of f of 0 to 2, 1, it's like a sort of a clopen arc in the unit circle, and that's not open in the unit circle, because you can't find this as the intersection of the unit circle with an open disk. And remember, S1 has topology induced from R2 by the subspace topology. So anyway, f is not open, so the image of an open set is not open. It just takes one to prove that f is not an open map, and yet it is an identification because it's a closed map, right? And we know that closed maps, in fact, give you closed identifications. So there's that. A perhaps trickier example, which I will leave to you guys. This is homework problem number 2 in Moncrief's. He has y, real numbers cross the reals, unioned with reals cross 0, a subset of the xy plane, if you will. And he takes h to be the restriction of the first projection map to y. And he says that you can show that h is neither open nor closed, but it is a quotient map, which means it's an identification, all right? And Moncrief gives the hint. He says, look at the inverse image of u. Well, he says if you take the inverse image of u intersect with r cross 0, you just get u cross 0. And so that's his hint. And here's the map that you're looking at. You want to argue that it's an identification, but it's neither open nor closed. It is, I think, relatively clear that it's continuous and that it's surjective, but you know, proving that it's an identification and proving that it's neither open nor closed, I leave to you guys. So anyway, there is an example. There's the example of one that's an identification but is not open or closed. All right, so moving on. Universal property of quotient maps is here. So lemma 5.6, if you have f from x to y an identification and g from y to z a continuous map, then there exists a continuous map h from y to z such that g is h composed with f, all right? And if and only if g is constant on the fibers of f. All right, so what that means, let's talk about what that means in the proof, okay? So so we suppose f is a quotient map, in other words, an identification, g is continuous, and then forward implication. Suppose there exists h from y to z continuous with g is the composite of h and f. Let y be in y, and suppose x1 and x2 are in the fiber of y, meaning that f of x1 is equal to f of x2. And our goal is to show that g is, our goal right now is to show that g is constant on the fibers of f, right? So here's two things in an arbitrary fiber of f. I'd like to see that g of x1 is equal to g of x2, and it's like taking candy from a baby. in the metaphorical sense, not in the actual sense, because if you've ever tried to take candy from a baby, it's actually very difficult. But anyway, so g of x1 is h of f of x1 by assumption of the composition, but these are both equal to y, so of course this is equal to that, and then that's g of x2, so g of x1 is equal to g of x2, which shows us that g is constant on the fibers of f. So there's the forward implication of the if and only if claim here, right? Remember to bring my white out today. Happy about that. All right, so next up, the reverse implication. Here we go. Suppose g is constant in the fibers of f. All right. Well, if x1 and x2 are in a fiber, for some, which map to some y, then that means that g of x1 is equal to g of x2. That's given, right? Now suppose y is in y, where y is equal to f of x for some x. Define h of y equal to g of x, right? Now that begs the question, how do we know that function's well defined? Because the choice of x need not be unique. So, well, okay, so if y is equal to f of x bar, some other x, right? Then x and x bar in the same fiber. Thus, g of x is equal to g of x bar, which shows you that h of y, so defined, is well defined. And then, if we suppose u a subset of z is open, we can notice that g, which is h composed of f, by the Sachs-Schutz formula, says g inverse of u is f of h inverse of u. But we know that g inverse of u is open by the continuity of g, whence h inverse of u is open as f is an identification, right? So the inverse image of a set being open means that that is an open set if f is an identification. So there you go, that's lemma 5.6. Now some examples. Actually, now an example. So here it is. We look at, and I've drawn some pictures for some low-dimensional cases, but I think that this construction rather beautifully works for n dimensions. So dn is the n ball, or perhaps you could call it the n disk. Probably n ball's better to say, but it is a disk in 2 dimensions. So x such that the norm of x is less than 1. And Sn we can look at as a subset of Rn plus 1, defined by taking, so this is a sneaky notation, see, because x is a vector and y is a scalar. And that's a typical point in Rn plus 1. And it is true that the usual n plus 1 Euclidean norm could be written as the square of the length of the vector part plus the length of the scalar part. This is really, embarrassed I haven't been using this already in other things I've done, because it's really slick. And I should use this more. Anyway, so of course, for a single variable, the absolute value, this is just absolute value, and so the absolute value squared is just the variable squared, like that. So that's a characterization of the n sphere in Rn plus 1. So like d1, for example, is closed interval minus 1 to 1, s1's unit circle, d2 is closed disk, s2 is the sphere in R3. And Minetti offers us this function dn to Sn defined by, he doesn't explain where this comes from or anything, he just writes it down, as will I. F of x is 2x times the square root of 1 minus x squared, comma, 2 absolute value of, norm of x quantity squared minus 1. Now, I think after we do some more calculations in this lecture, you can kind of discern where these formulas came from. Mostly in terms of when later in the lecture I'll calculate the fiber of these things, and we'll see that the fiber of these, it's mostly injective. Where it's not injective, it happens to not be injective exactly on the boundary of dn, and I think that's a lot of the reason for the formula. There's probably a simple geometric reason. I haven't really thought too hard about it. Probably if you broke these formulas down for like 3 dimensions and just stared at it for a bit, you could figure out what he's doing. But it does work. Here's the proof. I mean, this is a surjection. It's clear it's continuous because you're not having, the absolute value of x squared is excuse me, the norm of x squared is less than 1. So you're not getting into the, you get to 0 for the square root, but you don't get past 0. So these formulas are continuous given the context here. So that's okay. Why is it onto? I don't think that's immediately obvious. And here's the proof that it's onto down here. All right, so like to prove onto, you could just, basically pick a comma b in the codomain and try to solve these two equations, right? And so I did that, and so the second equation solves for a norm of x, gives you, square root of b plus 1 over 2, and then, okay, so then x is in the direction of a, right? Which means that x could be written as, well, the unit vector direction. Basically this is a hat, as you might call it in physics, right? The unit vector in the direction of a is a divided by the length of a, but I want the length, so this is the unit vector. I want the length of x to be square root of b plus 1, so I do unit vector times its length, that gives me the x, right? And notice that the length of a squared plus b squared is equal to 1 by assumption. So let's see, how do I know that? Oh, because it's an element of Sn, which is length 1, right? So the norm of a is a square root of 1 minus b squared. All right, so let's see if it works. Check it out. All right, here you go, guys. I don't believe these details are in Minetti because they're not interesting, but I don't know, they're interesting to me. Maybe to you, but a little bit below where Minetti tends to focus his energies. Let's see here, so that's fine. So here's f of this, I plug it in and work it out, and I get, a b over here because that simplifies down to b. And then here, when I plug in 1 minus the square root of 1 minus the norm of x squared, and this is 2 times x, right? So that simplifies to 1 minus b over 2 rooted. And this, of course, is 1 plus b over 2 rooted. But when you multiply these two, you get 1 minus b squared over root 2. But you get root 2, which cancels with that 2 and leaves you just this. But then the norm of a is exactly the square root of 1 minus b squared, so those cancel. And finally back, and here we go, ab. So I've just shown you that if you plug in this, you can output that, right? Now, to be there's a hole in this, right? Which is that my argument right here doesn't work in one case, does it? Like I see this in retrospect from future pages in this lecture, right? But technically speaking, you can't divide by the norm of a when a is what? When a is 0, right? So you need a separate argument to see that you actually hit like 0 comma what? What's in Sn? 0 comma what? 0 comma plus or minus 1, right? Remember, b is a scalar, but a is an n vector. So we need a separate argument. How do you get to 0 plus or minus 1, Well, I suppose you just, how do you get to 0, 1? Well, I think anything, well, I don't know how you get to minus 1. Huh. I'm not sure you do get to minus 1. Well, if I put the norm of x, if I pick any unit vector here, right? If I pick, let me scroll back down here. Sorry. If I pick any x with the norm of x being 1, then this drops to 0, right? And if I put norm of x being 1 here, I get 2 minus 1, which is 1. So we certainly can map to 0, 1. I don't think I can map to 0 minus 1, actually. Huh. I mean, unless I could put norm of x, if I could put the norm of x equal to 0, Can I do that? Oh, yes, I can. So if 0 is in Dn, right? So f of 0 is 0 minus 1, okay? And f of, let me write that down. So I guess I don't know where to put it. I don't want to mess up this sheet here. Sorry, guys. Just let me side comment over here, okay? So f of 0 equals to 0 minus 1, and f of anything with, well, let's just say this, f of the boundary of Dn is equal to the set containing 0, 1. So everything in fact in the boundary. And the boundary of Dn, what is that? Boundary of Dn just means the norm of x is equal to 1. So if you put norm of x equal to 1 into this map, you get 0, comma 1, right? Which you could think of as sort of like the north pole of the sphere. So yeah, this is interesting. So this function is 1 to 1, right? There's a unique point. Basically, this shows you that there's an inverse if we restrict it to the values for which. Oh, goodness gracious! If you stay away from 0 and the boundary, I suppose. Well, no, 0 is okay. 0 is just 1. One thing goes to 0, right? So every fiber of this map has just one thing in it, except for 0, 1. The inverse image of 0, 1 is the whole boundary of Dn. All right. Anyway, sorry, I don't know why I'm talking about that right now because it's more of an issue later in the lecture, and I just wrote these notes, so I'm sorry, I'm kind of getting ahead of myself. The larger point here is, okay, f is a surjection, great. Here's the rest of it that I didn't get here. So if it's a surjection, and what else? This is a surjection, this is compact, this is Hausdorff, it's continuous, therefore this is a closed map by that corollary 4.52. So since it's a closed map, it's a closed identification. Voila, we have an identification, okay? And there's a little bit more to notice here, which is that if we study f tilde, which is everything except for the boundary, then it maps to everything except for the North Pole. And this, okay, now this makes sense to me. So this f tilde is basically cutting the domain down and cutting the codomain down such that f tilde is in fact a bijection. And because every fiber has just got one thing in it, which means it's injective, and of course it's onto also by this conversation up here, which means that's a homeomorphism. On the other hand, and I don't know if you should really say f tilde here. Maybe I should just drop the tilde right there. F of the boundary then is equal to, I mean, okay, so technically speaking, I don't know, guys, you know, I'm going to try not to fuss at you so much either. But I do, sometimes I fuss at, you know, undergraduates who don't put sets where they're supposed to be. But it's an understandable shorthand, you know, so. Okay, anyway, so the larger point here is that f tilde, or f if you like, contracts the boundary of the n ball, dn, to a point on the n sphere. Since dn is compact and Sn is Hausdorff, I don't really need f tilde here. I could say f is a closed map, in fact a closed quotient map. All right, enough about this. Let us move on. That example will be returned to, all right, so. Hopefully more briefly next time we come back to it. So here we go. Quotient topology. Let x and y be topological spaces. Consider f a function from x to y and onto map. We define the quotient topology on y to be the only topology on y that makes f an identification, and the finest topology for which f is continuous. All right. So that said, what follows is what I mainly think about when I think of quotient topology. All right, so if we have an equivalence relation on X and you let pi be the natural equivalence class mapping, right, the natural map pi of X is the equivalence class of X, then the topological space X mod the equivalence, right, so the the space of equivalence classes is given the quotient topology in which pi is a quotient map. All right, and that is what's called quotient space. In other words, another way to say this is that to form a quotient space on a space, we need a equivalence relation. All right, and then for such an equivalence relation, the quotient topology on the set of equivalence classes is the topology which makes the quotient map continuous. So I find that easier to remember than all this identification stuff, personally, but whatever. So proposition, if f is a continuous map and tilde is an equivalence relation on X and pi is the canonical quotient map, there exists a continuous mapping from the set of equivalence classes to Y such that the composite of G with pi is f, if and only if f is constant on the equivalence classes of the equivalence relation. And this is hard to appreciate in the examples because in every single stupid example that we have, I think, the equivalence relation is actually given by the fiber equivalence of the map. And so like this sort of like indicates that, oh, there's this like equivalence relation and it exists on the space independent of the function. And then all of the examples that I have in this section, there's like a collusion between the function and the equivalence. So it's hard to understand what exactly is being gotten at here. It is, as he says, this is like basically a corollary to the universal property of the identification that we proved earlier this lecture. But here's the main application, all right? And this example 5 is really an example of examples. But anyway, so I'm not saying that this proposition doesn't have application. I'm just not so convinced it's been applied in this lecture, okay? Except in kind of the trivial sense of example 5. So let f be a continuous function, stability of fiber equivalence. So x and y are equivalent if f of x is equal to f of y. So notice that the inverse, the fiber is the equivalence class here, okay? Because the y which are equivalent to x means that f of x is equal to f of y, which is tantamount to saying it's the inverse image of f of x, which is, it's the fiber, okay? That might be overstepping my bounds. That seems too easy. So y is in here. Yeah, I'm not. Let me just erase that. I'm not 100% sure that's right. So let's just less is more. All right, there we go. Okay, so by the proposition above, we induce from F a continuous one-to-one map on the quotient, like this, and we notice that F is an identification if and only if F bar is a homeomorphism. So yeah, let's see how that works. Well, actually, we'll come back to how that works. First up, though, we have yet another way of looking at the quotient space, which is more often how it's done. I mean, this identification stuff is lovely, but I think in practice, I almost always think about quotient space as I'm showing you right here. So let A be a subset of X and consider the quote-unquote smallest equivalence relation on X by taking A as an equivalence class. All right, so X is equivalent to Y if and only if either X is equal to Y, all right, or X and Y are in A. So we denote x, the set of equivalence classes of x by tilde by x by a, all right? So here's an example where we'll put that into practice a bit, although it's going to be a bit. So consider f from the n-1 sphere across the unit interval to the n ball defined by f of x comma t equal to tx, right? So pretty clearly this map is continuous, and I guess it's fairly obvious it's onto. I might prove that down here. I don't know. I think I do. I think I proved the onto down there. So we'll come back to that. All right. Notice that this is the Cartesian product of compact sets, which is thus compact, and also Dn is Hausdorff. Therefore, f is a closed map. And taking out a logical loan here for a second, if you'll indulge me to assume that f is onto, then we have that as a closed identification. But f is not injective. Its fibers are solutions of tx equals to y, where y is in Dn and x comma t is over there. So I wanted to understand what the fibers of this map look like. That was what I was after here. So let's see. I think I inadvertently proved that it's. Do I prove it's onto? Maybe I don't prove it's onto. Goodness. I suspect we could see onto from these things I calculate down here. Let me just boot this up here to where we can see all of my jibber jabber. Got everything in frame there, more or less. All right, so make sure we see it. Yeah, we can see everything. All right, so let's see here. I guess I can make do with that for now. So this is the domain. This is the formula. Let's see here. So if f of x comma t is equal to y, right? My question is, what is what choice of x and what choice of t are going to give me y, right? So x is an n-1, so the norm of x is 1. So the norm of tx has to be the norm of y, which tells me that the absolute value of t has to be equal to the norm of y. But t is non-negative, so the absolute value of t is just t, which means my choice of t is the norm of y. And so I've got norm of y times x is equal to y, which tells me that x is just it's just the unit vector of y. Okay, so this is all a very dumb calculation, right? I essentially did this by intuition a little bit earlier in this lecture. Hence, we calculate that the inverse image of y is exactly this, right? Provided y is not equal to 0. But on the other hand, the inverse image of 0, what maps to 0? Well, you can put anything. So since x is taken from Sn, 0 is not an option for x, right? Because the norm of x has to be 1, length 1. This is the n-1 sphere. 0 is not on the sphere. So x can't be 0 in this formula, which forces us to put t equal to 0. But on the other hand, x is completely arbitrary. So the inverse image of 0 is actually the n-1 sphere across 0. This is where injectivity is lost. But on the flip side of things, you see that we can get any thing in Dn, I believe. I think this is essentially proved onto if you sort through these calculations, because if I take y in Dn, right, then I can pick I can pick t to be absolute value of y. I guess the only thing I'm missing here is that since you're in Dn, that means that the norm of y is less than 1, right? Which means I can always select. I have to be able to select t appropriately, and if norm of y is less than 1, that means t is less than 1, which it needs to be, right? Because t has to come from here. So anyway, I think it's okay. I think we proved that this essentially proves it's onto, and it's not injective, but that's okay. So, but I was trying to look at the fibers because I wanted to understand them, right? So in summary, if we look at A as being the n-1 sphere across 0, the fiber equivalence for the map F is that you can think of it as, I just use different letters to get them, free us of the x's and the y's. Z is equivalent to W if and only if either Z is equal to W or if Z and W are in A, right? And so going back to the example 5, the mapping that's induced from F onto the set of equivalence classes here, right, is what it's doing, right, is it's the equivalence relation. It's essentially just saying every point's equivalent to itself, right, unless the points are in A. And the points in A are exactly this set, right? So the F bar is from this mod that to Dn, and that's going to be a homeomorphism. So an example of this would be for like, n equals to 2. If we look at n equals to 2, we're doing, S1 cross the unit interval, which you could think of as a finite cylinder, right? You're just taking a stack of circles like this, right? And the equivalence is saying, the fiber equivalence of this map is saying that every point's its own point except for A, and the whole base of the cylinder is getting squished to a single point in the equivalence class, right? Which you can think of as sort of, it's taking the cylinder and turning it into a cup. But if you think about a cup is homeomorphic to a disk because you can just kind of bend the walls of the cup down. And this is, to be clear, this is the the closed disk. So, and the sides are included here too, right? I don't want to mess up my picture, but fine. Right. This is not, I don't know, it's not solid. It's just the edge of it, not the inside of it. I don't know. How do you indicate not solid? But I guess you got to say it with words. So there, I did it. All right, my job is done. Moving on. 7 here. Example 7. Page 7. Talk about the hypercube, and then the boundary of the hypercube, and we want to look at its quotient space of the hypercube mod its boundary. So a few things. We remember that before we proved that the unit interval is homeomorphic to, well, I mean, it's kind of funny. I1 is technically equal to, oh no, that's not true. I1 is 0 to 1. D1 would be -1 to 1. So I guess they're not exactly equal, but they're pretty close. Anyway, we can prove that, and we have proved before, that the the hypercube is homeomorphic to the n ball. All right. And in example 4, we learned that f from dn to sn was an identification, and that induced a homeomorphism f tilde from here to here. That's lovely, but that's kind of not the point at the moment. So let's take a step back here. What does it give us? That it's an identification. All right, let me just sort through it here bit by bit. So we have f from x to y continuous and f an identification. Then that gives us that f from the x mod the fiber equivalence to y is a homeomorphism. But what are the fibers of this exactly? Well, I just was sorting it out with you guys earlier, but basically x is equivalent to y if and only if this is equal to, with x's is equal to the same thing with y's, which gives us two equations. The top one's a vector equation, the second one's a scalar equation. And to be clear, bad notation here. This guy is equivalent to this one, okay? And then this, okay, well, hopefully you can, let me just talk through it. So this is equivalent to that, so we can solve this for norm of x equal to norm of y. and then I've got, I divide the 2's out, I've got that, but of course, since these are equal, that actually just gives us x is equal to y, so we got norm of x equal to norm of y, and x is equal to y. Well, assuming that the norm of x is not equal to 1, right? Norm of x equal to 1, I can't make this jump. So either, these are equal, means either x is equal to y, where norm of x is not equal to 1, or that the norm of x and the norm of y are both 1. That's how we solve this equation, right? Okay, so in short, the inverse image of x, if the norm of x is equal to 1, it's exactly the boundary of dn. And so what we have then is that the induced map f bar from dn mod the boundary of dn to Sn is a homeomorphism. But we also know that since In is homeomorphic to Dn, then a space mod its boundary is homeomorphic to to a homeomorphic space mod its boundary, which gives us this. So I do think there's a little bit of a jump there. I don't know as we've actually proved that, but you could. You could. Let's see here. So next up here we have the Mobius strip. So of course I would be negligent if I did not, show you the Mobius strip like a civilized human being, which is to actually take a strip, right, like so, probably too thick, but oh well, we'll make do. So take a strip here, right, and just take it and twist it, right? Now let's see if I can twist it. Oh man. Alright, let's try that again. Still too thick. Too thick. So maybe try quarter. Maybe a quarter of this paper will allow me the pleasure of forming a Mobius band. Alright, so here we go. So we got a strip, take it. If we did this, if we, if we glued these two pieces together, right, we'd have a cylinder, right? So if you just twist once, like that, then this is a Mobius band, right? And the interesting thing, of course, about a Mobius band right, is, if I can get this. So I put the purple on one side and I put the green on the other. Let's see what happens when we twist. Alright, so here we go. Purple meets the green, right? So we start our purple, and then we're going to follow it, right? Follow it, inside. It's hard to follow it inside, but and then it goes green in here, right? You keep following it, and then the green comes back out over here, and then we're back to purple again, right? Oh, I'm sorry, I keep going out. Anyway, the point is, if you follow it, you'll find out there's only one side, right? The two sides have become just one side, right? So the Mobius strip is a one-sided surface. That's kind of weird, isn't it? So one-sided surface is a surface which can't be oriented, right? So if you want to talk about integration on something like a Mobius strip, then you need to, well, you need to do some things. You need to make some ad hoc choices, I suppose. But anyway, let's go on here. So I've lost my cover sheet here. So more formally, a Mobius strip you could think of as taking the unit square and forming the following equivalence. Basically, every point is equivalent to its, like the equivalence class is every point's on its own, except we identify. Let's see here. Oh man, shnikes! I forgot. I was going to erase that. Sorry, guys. There we go. Now it's better. So we have 0y is equivalent to 1 comma 1 minus y. So I did some color coding over here to show you the equivalence, like 0, 1 equivalent to 1, 0 is equivalent to 1, 0, 0, 0 is equivalent to 1, 1. This purple dot gets glued to that purple dot, this orange dot gets tied to that orange dot, and so like that's the, the twisting formally is we're forming that's our equivalence relation, and then every other point's just equivalent to itself, right? So and so that's the Mobius strip as a quotient space. It's x by, x mod that equivalence is the Mobius strip. And here's another way to visualize it. You have, it doesn't have, I said the unit square here, that's just a choice, right? You could take a strip like this and identify like that instead. And there's a lot of different variations on this idea. You can, I know you can do like one twist or you can do multiple twists. I'm not sure how to do the multiple twists in this stuff we're doing right now. So I'm just saying that this, what I'm trying to tell you is that this discussion of Mobius strips is incomplete. All right, that's all I'm saying. This is definitely a construction of a Mobius strip. Is it? How do you construct every Mobius strip? No. All right, no. Klein bottle. The Klein bottle, you take the unit square and identify, glue together the edges, flipped, right? The one up, the one down, those tied together. And then you also identify the top and the bottom in the same orientation. So you can draw these arrows like this to indicate that. A more careful way of saying it is that 0y is equivalent to 1 minus y, and x0 is equivalent to x1 for all xy and 0 to 1, and all other points are equivalent to just themselves, all right? But if you say that you have the green and the orange equivalents, it does imply that the four corners are identified, right? Now, I should mention, I haven't written this out in the notes. Maybe it's a homework problem, I hope. It's like yelling at me. It's just, I'm having a hard time not writing it down, but I'll stop myself. So if you, instead of disorienting these two sides, if you just glue them together in the same orientation, then that gives you a torus, right? So yeah, if you like just kind of take a sheet and then sort of bend the sides. Oh, I can't do it with my hand, but anyway, well, no paper can quite do it, right? This gives you the cylinder, right? And then if you could somehow imagine bending this side around to that side, if you had more like a rubber sheet instead of this, you can imagine kind of if you could identify this side to that side, you get a torus. I think if I did it right, I think that's a torus. Is that a torus? I feel like it's a torus. I could be wrong. Maybe I'm wrong. Maybe that's not a torus. Well, anyway. See, this is why we can't have nice things. All right. Anyway, so leave that to the comments. Is that a torus? Let's see here. Finally, a quotient. He mentions at the end, quotient of compacts is compact. Quotient of connected spaces is likewise connected. But Hausdorff spaces are notoriously ill-behaved with quotients. So if you have an identification where x is compact and y is Hausdorff, well, that's a lot. Then the following are equivalent. X, not y is Hausdorff. X is compact and Hausdorff domain. Then the following are equivalent. Y is Hausdorff. F is a closed identification. All right. And K, which is this lovely set down here, is closed in the product. So let's see here. So why being Hausdorff would indicate that the quotient space is Hausdorff, right? Because if you look at F bar from X mod the equivalence, that's homeomorphic to Y, right? If it's an identification. So if Y is Hausdorff, that would mean the quotient space is Hausdorff. So I guess if you have an identification from a compact Hausdorff domain which is also a closed identification. It follows that the quotient space is Hausdorff. So if you have enough goodies, you get Hausdorff. But generally speaking, getting Hausdorff for the quotient is tricky. So beware of that if you find yourself on a research problem where you need your quotient to be Hausdorff. All right. But I'm not trying to be too sophisticated about it here. I'll let you look at the proof in Minetti here, and we will go on to the next thing, which I think is, I forget, I believe up next is quotients by, let's see here, quotient groups of homeomorphisms, section 5.3, and then I'll try to do a lecture on that and projective spaces next. That would be my goal, to make you one lecture that does both of those as efficiently as I can. All right, so anyway, that's where we're going. So thanks, guys.